Okay, it's 11 o'clock, and I would like to welcome you all to the event From Global Climate Modeling to Climate Information and Climate Adaptation. Welcome both to those of you that are here in the room and those that are following us on the net. My name is Roar Skålin. I'm Director General of the Norwegian Meteorological Institute, and I will be chairing this event. And I'm joined today by 6 esteemed climate scientists. 5 of them will deliver presentations, and all 6 will participate in a panel discussion at the conclusion of this 90-minute session. Earlier this morning, the AMEP Arctic Climate Change Update 2024 was presented in the room next door here. That report highlights the rapid changes occurring in the Arctic and the impacts on the cryosphere, hydrology, and ocean acidification. This changes underscores the urgent need for enhanced knowledge to support our Arctic adaptation and to understand the progression of climate change. This essential knowledge is derived from long-term observations and projections from global Earth system models. One such model is the Norwegian Earth System Model, NOR-ESM, collaboratively developed by the Norwegian climate research community. NOR-ESM serves as a crucial tool for climate researchers, and its simulations have been extensively utilized in research and as input for IPCC reports. And in this side event today, we will present the latest results from NOR-ESM and delve into pressing research questions concerning the Arctic region. We will explore the value chain from global climate modeling to regional and local information, with a particular focus on polar areas and the Arctic. Some of the key questions include: how can we effectively transfer climate change knowledge from science to services relevant for the end users? How can the information provided by climate models be adapted for local and regional planning and management? This event will commence with 5 presentations, each approximately 8 minutes long, followed by a brief Q&A session after each presentation, so I will allow for at least a couple of questions. And subsequently, we will have a panel discussions. While we have prepared some questions for the panel, we encourage you to actively engage by posing your questions. And we particularly invite you to challenge the panel on how society can better utilize their knowledge and the findings from climate simulations. Additionally, we welcome your comments on areas where you believe further knowledge is necessary. Thanks for joining us, and we look forward to a stimulating and insightful event. We will start with an overview of climate modeling with NOR-ESM. It will be given by Michael Schulz. Michael is a climate scientist at Met Norway. His expertise is in climate modeling, particularly related to the interactions between aerosols, atmospheric chemistry, and climate change. He has worked extensively on the impacts of aerosols on climate systems and contributes to improving climate predictions through advanced modeling techniques. So please, Michael, the floor is yours.
Can do from climate modeling. So I'm intending to start with some introductory slides, some highlights, and some reflections on what NOR-ESM is and how maybe it should be used. And then we have presentations on cloud, sea ice, assimilation, and downscaling. So there's a range of presentations. I hope you enjoy it. I'm Mike Schulz from the Norwegian Meteorological Institute. I'm leading the model development at Met Norway and co-leading it together with a colleague from NORS, Mats Bensen, in Norway. We are, maybe just for those who are not familiar with what a model is, a climate model, from a scientist's point of view, it is something we have to document and use. And in simple words, it's computer code, which is based on the work of a lot of scientists. You may call it a cathedral, a modern cathedral, because it's really containing code and experience and parameterizations from hundreds of scientists. So we are, for instance, using the American NCAR CSM model as a base and have developed it further to Norwegian needs and Arctic understanding. We are lucky that we have a cooperation in Norway. We still have a lot of cooperation internationally, but you see here on the bottom the institutes which are contributing from Bergen and Oslo, but there are also other users in Norway, Sweden, and who really use the model. So what is on the mind of climate modelers? And I picked this graph to just give you a flavor of what scientists have in mind if they want to upgrade the model. So we had one model which was contributing to the last IPCC report, CMIP6 experiments, and we are in the lucky position that we are now starting a new upgrade phase, supported by the Norwegian Research Council and an infrastructure project, INES2, and a research project, NORIS-M for CMIP7, lasting 4 years and prolonging after that. But just these images, if you can see them, show a little the flavor of what we are thinking about. We have to refine the grid. We want to get to finer grid. We want to improve chemistry in the stratosphere, in the troposphere. There is an idea of improving the knowledge on ecosystem dynamics, having the vegetation be more dynamic in the model, keep tracking forest fires and their impact on the carbon cycle. There is now Antarctic and Arctic ice sheet dynamics submodel in the model. We do have a lot of technical things, which you are maybe not so interested, but we're also thinking about a different sea ice model. Aina will talk a bit about sea ice developments, ocean waves, and then the methane and nitrogen cycle are important to understand the evolution of the carbon cycle in the future. So that's the insight a bit into what we are thinking. I thought I select 2-3 results how we used it in the last round. So one picks a bit upon what we just saw in the AMAP session. The sea ice decrease observed by satellites is a record which goes back to the 80s and to the present. And we have an understanding of winter and sea ice and summer sea ice trends. This is the black line on these figures. And what we are interested in is, of course, when in the future will we consider the summer sea ice free, and that is what we get from these scenarios. So there were a range of scenarios prepared, emission scenarios for the future, more or less greenhouse gas emissions with associated other co-emitted species aerosols. And what you can see from this figure is that all of these scenarios really will not change the trajectory for the next decades. Until the mid-century, we expect that in these worlds, in these virtual worlds, there is a ice-free summer in at least the high scenarios. Maybe the low emission scenarios stay a bit above, but still we expect that sea ice in summer is halved by 2050 in all these scenarios, unless we really get to very low emission scenarios. So that is, of course, an important finding from these climate model simulations, because it gives us both a timeline and local information if you go deeper into the regional spread of sea ice. The second example is maybe something which you have encountered here and there is that, of course, the climate models not all get to the same result. So a common metric of that is that the climate sensitivity of the models, so the temperature increase as a function of increase of CO2, is different in different models. Models warm differently. And there were different assessments, as you know, from CMIP going into IPCC. And in the latest IPCC report, this range of estimated warming in the future has increased. And IPCC took then other information to basically say that probably the models were exaggerating that range of uncertainty. And just back to Norris M, we had a very peculiar situation that our American sister brother model CSM had a very high climate sensitivity, and Norris M a quite low one. And that was, of course, very interesting because the models were very similar. And in the end, it turned out that the interaction between the ocean and the cloud fields in the southern hemisphere, the Antarctic interaction of ocean circulation and cloud feedbacks, were the culprit. So the CSM warmed much quicker in the upper ocean temperatures, and that created less clouds and more quick warming in the CSM2 model than in the Norris M2 model. So having different models also gives insight into important processes. So it is a paper which really also triggered, among others, the importance of studying polar regions and temperature evolutions like Antarctic ocean circulation together with the coupled system. So what is really motivating us right now is that it looks like the last 2 years were very warm. You have all seen these records of temperature. To the left, the sea surface temperature of the last 2 years. On the right side, the air temperature. And those 2 years were pretty outstanding. And it is hard to just explain it with El Nino. So are we living in an era of accelerated warming? I think that's a question we need to explore both from the observational but also from the model side. We have to test in the model different hypotheses, and that's what we intend to do, because there are different hypotheses on why this is happening. Either we don't understand the feedbacks, either it's just a sign of internal variability on top of a trend, or some of the forcing have changed. There was a decrease in aerosol emissions. There was a cut in ocean sulfur ship emissions. There was a Honga Tonga volcanic event injecting a lot of water vapor in the stratosphere. So there's a range of hypotheses which you want to understand, and I think that's a motivation for having a model to test hypotheses. And then the second question, of course, is on top of that, there's Arctic amplification. As you have just also heard in the ARMAP session, if you have been there, there is a projected 3 to 4 times increase in temperature in the Arctic. And if you look closer into the map to the right, this Arctic amplification of end of the century temperature over 2015 temperature is not homogeneous. So there are regions which are probably warming more than others. So if you're interested in where this Arctic amplification is most intense, I think these kind of maps are very useful and interesting and can be delivered from models. So I just have 2 more slides, one on how the model is in the end used. I think one aspect of climate model is that the results go into reports. It is summarized, it is compared with other climate models. It is ending up in IPCC reports, maybe a bit drowned, but it is prominent for future scenarios to have a model. But maybe we should discuss maybe a bit more in the end how it should be used. And I think there are two main fields of how these climate models can be used, should be used. One is the impact quantification. So where exactly does climate change hit? One example, what is the difference between 1.5 and 2 degree world? What is the impact of an overshoot of emissions in the next decade if we do not manage to reduce emissions in time? Do we maybe have to better downscale, visualize these effects? And the second aspect is really that we still need further climate understanding. Are there any uncertainties, abrupt changes which we have missed, like what I just mentioned? What is the reason for accelerated warming? The carbon budget is computed in these models, so we have a lot of knowledge in the models which we probably don't use perfectly well, because we have also the challenge to get the data out again after the model has been run. That is what I had in mind, and I think I finish here. Thank you very much.
Thank you, Michael. We have time for a question too, if you have questions for Michael. The panel debate. Next presenter is Trude. Trude is a professor at the University of Oslo, and her research primarily focuses on the role of clouds in climate systems, with particular attention to their interaction and effects on global warming and climate feedbacks. So, Trude, you have also managed to get the word clouds into your presentation? Yes. Always. It is cloudy with a chance of rapid warming, and NORISM view on factors contributing to uncertainty in future Arctic warming. Please.
Thank you very much, Struve. You may hear in the context of discussions about climate change that the science is settled. And maybe that is true in the sense that we know that for all known and plausible scenarios, we have to prepare for strong warming in the Arctic. But considerable uncertainty still remains, and I think for policymakers, decision makers, they need better information than that. They need to know how much warming to prepare for so that they can set targets for mitigation or know what to adapt to. And so that's the sort of the message of today's presentation. I'm going to talk about how we can use NORISM as a tool to probe this uncertainty and look at what possible future Arctics we may have to prepare for. I have a long list of co-authors and contributors to what I'm going to present, and so instead of mentioning people specifically, I just put below here a long range of contributors from UIO, Met Norway, UIB, and NORS, and so on. The title is, as many of you have recognized perhaps, a wordplay on this animation movie, Cloudy with a Chance of Meatballs. And so in that movie, if you've seen it, you know that it's an example of how use of technology can sometimes go very wrong. So maybe a lesson to be learned from that. Moving on, so you will have heard probably this morning several times about Arctic amplification. And so that's simply the ratio of Arctic warming to global warming. And I'm showing you in this graph in red the observed Arctic amplification since 2000, and you can see that it's been increasing considerably. So the warming that we experience in the Arctic relative to the global warming is increasing. And we see that the observations are now starting to move out of the envelope spanned by the model simulation. So we have the two last generations of climate models presented here in gray spaghettis, CMIP5 and CMIP6, and you see that very few, if any, models simulate an Arctic amplification of around 4, which is what we're now seeing in the observations. And so we're starting to worry about whether our models are missing something important, specifically for Arctic climate. And so one important source of uncertainty for Arctic climate projections is clouds. So we know now better than we used to, because we have fantastic satellite measurements now from active remote sensing, so LiDARs or radars in space. We now have a very good understanding of the cloudiness in the Arctic, and we now know better than before that the Arctic is a very cloudy place. What we also know is that clouds, contrary to the rest of the planet, or most of the planet, clouds have a warming effect for most of the year in the Arctic. So clouds tend to cool by reflecting sunlight back to space for most of the planet, but in the Arctic, because it's dark for most of the year, the clouds have a warming effect. So the Arctic is much, much warmer than it would have been in a less cloudy or cloud-free Arctic, if we could imagine that. And so therefore, it's also clear that if clouds were to change as the Arctic warms, that could have a strong impact on the rate of warming in the Arctic. It's also true that our climate models tend to be adapted to measurements that are made outside of the Arctic, and that's simply because measurements within the Arctic have been very scarce, right? So a lot of processes that we try to represent in climate models, we have tuned or adapted to measurements made in low or mid latitudes. And we think that's a serious problem in some respects. So I show some examples here of measurement campaigns that we've recently conducted. One aircraft measurement campaign, so I'm showing you aircraft tracks there out of Andøya in 2023, where we took a research aircraft and measured in clouds. And we also did the same in an earlier campaign in Ny-Ålesund. So we had tethered balloons, among other things, that allowed us to measure in clouds. And one thing that we measured were particles that influence clouds. Specifically, they influence how much ice can form in clouds, which is going to turn out to be very, very important in the story here. And so what we found was that you see this red dotted curve at the top of this graph. This is the concentration of ice-forming particles that was in the model originally in Norge-SM and in many, many other climate models as well. And below are measurement points and fitted lines for our measurements from these campaigns and other campaigns. And so we see that we have dramatically overestimated the amount of particles that can form ice in clouds. And note there's a logarithmic y-axis here, so we're missing this by a factor of 10,000. We had about 10,000 particles too many. And so maybe you're thinking, so what? Why does this matter? So I'm showing you here that as you would expect when you correct for this, you produce, on the right here, we find in Norge-SM that when we have more correct particle concentrations for the Arctic, we find a lot less ice in the clouds. This is exactly as you would expect. And we also find that you gain more liquid, which is what we're seeing on the left here. So all year round, we're gaining more liquid in the Arctic clouds, but especially in the winter, where before we made this correction, the clouds were all ice. And I think I'm going to skip over what I'm showing on the right there, but we find also that there's now better agreement between satellite measurements of phase and what we model. So we think we are definitely also moving in the right direction when it comes to comparisons to satellite observations. But I wanted to get to what this means. So when we have made this correction based on Arctic measurements, instead of using measurements from outside the Arctic, we also get a model that is much more responsive. We get clouds in a model that are much more responsive to warming. So now we get clouds that are spreading out, that are increasing in amount with warming. And so what we're simulating then, and this was a nice coordinated experiment with Norge-SM, we ran many sensitivity experiments where we made changes to the models that were not just sensitivity tests, but also we made changes that we thought were the right ones. For example, with respect to clouds, we made this change that I just talked about, but there are a number of other changes as well, but I'm particularly interested in the cloud story here. And the gray curves here on the left figure show the original, sort of default NORISM simulations for different emission scenarios. So you can see that we followed this high emission scenario when we ran the sensitivity experiment, but we got much more warming in this experiment that is called cloud, where we made the corrections based on the Arctic measurements. And so now you can see for the high emission scenario, at the end of the century, we get something, well, 5 to 6 degrees more warming in the Arctic with this correction that we do think is for the right reasons. And on the right here is a sort of a comparison in the pink shading, we're showing the range of warming that you could get if you just vary or change these things that we think are changes for the better in the model and get a very wide range. And it's actually as wide as the range that you get if you just try all the kind of established emission scenarios. So this uncertainty here is as important as the uncertainty when it comes to what we do with emissions, whether we follow a low emission path or a high emission path. So to conclude, this sums up what I've just been talking about. We are concerned that climate models, including NORISM, may be underestimating Arctic amplification. And this might be because the models are missing key processes or misrepresenting key processes, possibly because they are generally adapted and tuned using measurements made outside of the Arctic. When we do use measurements made in the Arctic and we make corrections to the model based on them, we find a much stronger Arctic warming. And I could go into the mechanisms if you want to, you could ask me about that. But important to end with here is that this has really important implications, of course, when it comes to what we have to be prepared for in the future Arctic. And also, I think, highlights the importance of going to the Arctic and making measurements there and kind of constrain our models with that. So with that, I'd like to end. Thank you. All right.
Or perhaps even 2. Oh. So Michael told us about the next phase of, or at least he showed the next phase of NORISM. My first question is this something that you will incorporate into the next version of NORISM? And the second one is, are there other parts of the globe where you see similar issues with the clouds, such as, for instance, in the Antarctica?
The quick answer is yes and yes. But yes, we are starting a nationally coordinated project now, focusing on NORISM development and to test NORISM against things like this. And so this will very much be a theme in that project as well. And certainly Antarctica is similar to the Arctic in this way, in the sense that it's a very clean and pristine special environment. There are many differences between the Arctic and in Antarctic, but this is maybe one area that is where they have something in common.
Thanks a lot, Trude. No one else? No? Okay, so we have been in the atmosphere. Now we move down a bit and to the interaction between the atmosphere, ocean, and ice. And that will be presented by Einar Olason. He's a researcher at the Nansen Environmental and Remote Sensing Center, NERSC. And Einar is an expert on sea ice dynamics and numerical ice sheet modeling at the basin scale. So please, Einar, floor is yours.
Yes, here we are. Right, so yeah, I'm a sea ice modeler, first and foremost. And I wanted to talk to you now a bit about what we call atmosphere-ocean ice interactions. And the first slide is, of course, what you mean when you say this. So in the Arctic, a key characteristic of sea ice is that it's a very, very good insulator. So whenever you have sea ice, you're basically blocking any impact that the ocean may have on the atmosphere and vice versa. So if you have a completely unbroken sea ice cover, it means that there is almost no interaction between the ocean and the atmosphere. So the ocean is relatively warm. It's -2 degrees or so, or the atmosphere can be at -40. But when you break the ice, then you suddenly have a contact between the atmosphere and the ocean. And in the image here on the right, you see a lead where the ice is broken and drifted open. And even it's a satellite image, the lead is about 20 kilometers wide, but we can see in it, we can see the clouds that form when the warm ocean is in contact with the cold atmosphere. The moisture is pulled out of the ocean, and a lot of heat is pulled out as well, and you get ice fog, and you get new ice forming along the edge, which is blown across. So once the ice breaks, a lot of things start happening in this other very quiet and calm environment. And we know and we see that this is very important on a local scale, but to try to understand it, the impact of these kind of interactions on a basin scale or even a global scale, we need models that can actually represent these small scale processes. And well, that's what I'm working on, essentially. And that's what we said, Michael said earlier, this is the new CS model that we want to introduce in the NORASM model. That's the one that we are working on. And the key question behind this all is how broken up is the ice? Is it actually something that happens all over the place, or is it just a few places here and there? And in a classical CS model, the ice looks like this. It's just a white cover. It doesn't really do anything very much. Okay, and the more sort of the usual image we have of the ice is something like this. This is from the drift of the Fram back in the day. Lots of very compact ice ridges. Here's a more recent one from the Nansen Legacy project. Again, a very homogeneous and flat kind of sea ice cover. But if we go out a bit, if we go up into the atmosphere, and here's a drone figure or an image taken from an airplane from NASA, you can start to see that there's a lot happening actually. There's a lot of features, and all the crisscrossing lines you see in this image are ridges or leads where the ice has broken and either drifted or started drifting apart or started crushing together. And when you really go out, you can get images like this. And this is the shear motion from satellite. So the yellow parts are where the ice is intact and floating as a single big flow, and the blue lines, the very narrow blue lines, are where it is broken and is shearing like this. And actually, this kind of thing, it changes a lot. So the images come about every 3 days, and you can see as soon as the atmosphere changes a bit, the ice breaks in a different way. So these patterns are very typical of what we see in sea ice in winter. And all these lines, they are leads and ridges. They are where the ice breaks and where the atmosphere and ocean start to interact, really, in the Arctic. So that's what it looks like in reality, and here's what it looks like in a typical climate model. So on the left are observations, and in the middle here is a sort of traditional kind of climate model, the type of sea ice model that's used in climate model, and you can see it's all sort of smeared out. And in this kind of model, we wouldn't see a lot of interaction between the ocean and the atmosphere in the model. You'd have to somehow prescribe it or force the model or tell the model that there is something there anyway. And people have tried that, but it's not really, well, it's not a very nice thing to do, I think. It's not, but so what we've been working on is a model that can actually represent these kind of motion of the ice. So now here in the middle is the new model that we've been developing, and it's a result of a 10 or 15 years amount of work at the Nansen Center and also with collaborators in France. And if this, I should probably mention also, I should mention the CESIP project, which there's a nice poster on that in the afternoon if you want to have a look, which is a large collaborative project on developing this kind of models. And it's on the back of this huge amount of work that we can now step up and say, okay, we are ready to start to put this into climate models, and one of those will be the NORI-SM. And then we can start seeing what happens. But of course, we started already, because you can't keep, so we took the NextSim model that we've been developing and coupled it to an ocean model. And running this for a 20-year simulation, which is on a climate scale, is very short, actually. But it's still much, much longer than anyone had done before. And we can see some very interesting things. So here, in this animation, the blue parts are where there's not a lot of new ice formation. And new ice formation is kind of our key measurement of how much heat the ocean is losing to the atmosphere. Because as soon as you open up, the ocean loses heat and it freezes. So you form a lot of new ice whenever there's a lead. And this mirrors basically the image I showed before, where the atmosphere is rolling through, breaking up the ice, opening it up, and there's a lot of new ice that forms in the center of the Arctic there. And interestingly, in the middle of winter, about 20 or 30% of all ice that is formed in the Arctic is formed in leads. And I think even more interestingly is this percentage is growing. So in this relatively short run that we had, it was already growing for about 25 to 30%. So things are changing, and we can see it in the interaction between ocean and atmosphere, in this very limited example, but also in lots of other examples as well. So to conclude, for me, what makes sea ice interesting are these structures. Leads and ridges, that's the difference between a blank page and what is really sea ice. And to get to understand how this impacts the other media and the entire climate system, we need good models. And one of these models is the NextSim model that we're developing. That will be in the NORI-SM. That's one of our future goals, like Michael was talking about. And a final point I wanted to make is that when the climate is changing, we need to understand really the underlying processes that are happening. You can't just take you can't take a simplistic model that is based on current observations and apply it to the future, because things are changing so much. You need to really understand what's going on. And this new model is essential to really understand atmosphere-ocean ice interactions in the future Arctic. Thank you.
Thank you very much, Einar. I will ask again if there are any questions for Einar. I don't see anyone here, but I have one for you as well.
Yeah.
In order to improve my understanding, in one of the pictures or simulations you showed from satellite images, the way I saw it, it changes really fast, even more or less from a day to day.
Yes.
So that's correct?
Yeah.
Yeah?
Yeah. It really, is this one?
Yes, that one. Yes. It doesn't show there, I
it
think.
doesn't show there.
No, we can see.
Yeah, it's this one. Yes.
Yes.
Yeah. So no, it really changes, and you can really see the impact of single weather events on these cracks. You can see how the low pressures or how the storms are coming in and breaking things up, and how they move around. It's really quite reactive.
So for me, also working with weather forecasting, does a model like this also, you think, can it be used also in weather forecasting?
Yes.
Yeah.
I think for me a very interesting long-term goal would be to use the patterns that you see in the ice, because you can see them from satellite, as sort of boundary conditions for the weather, because then you can fit the surface winds to what happens in the ice. So you have a kind of an observation of the surface winds there already.
Yeah. Thank you very much, Einar.
Thank you.
So, next presentation will be given by Tore Furvik. Tore is the director of the Nansen Center, so the boss of Einar, and is also the former director of the Bjerknes Center in Bergen. And his research focuses on oceanography, climate modeling, and the interactions between the oceans and the climate systems. And he will be covering two topics, data assimilation and as well machine learning methods in climate modeling. So please, Tore, floor is yours.
Thank you very much. And I think I'm a little bit on thin ice here because this is not something that I've been working on in depth myself. So this is mainly work by François Cugnot at the Nansen Center, who is leading the climate group. And so we talk about data assimilation we are doing, I will talk about machine learning we are doing now, and I also talk about new methods and how we are sharpening our tools to make more faster prediction and also more accurate predictions. And just one slide describing the Nansen Center. I often use this one. So what we are doing at the Nansen Center, we are out in the field doing observations, and we are also working extensively with remote sensing data from satellites. So we have very good collaboration with ESA, European Space Agency. And what we are doing, and what we are doing very well at the Nansen Center, is to take observations and bring them into models. And that's what's called data assimilation. I'm coming back to this. And then we are running models of ocean. We are running models of biology in the ocean. We are running models of sea ice, as Einar showed. And we are doing this both operationally, so we are doing this for the European Copernicus program, the Arctic Marine Forecasting and the Monitoring and Forecasting Centers. We are doing it operationally. And we are also doing this for climate research, as was shown by Einar. And just one slide about timescales or memory in the system, because this is important for what we can actually be able to predict. So the atmosphere, you can just think about the goldfish with a very short memory. So that means that if we know the weather today, we can predict or forecast the weather perhaps a week, perhaps 10 days, perhaps 2 weeks into the future. It's a short memory in the atmosphere. If we know something about the soil moisture, or snow, not snow, ice on lakes, not ice on lakes, we have the ability to make predictions for some longer time, into months. But if you're really going to say something about what will go on next year, next 10 years, then we need other information. That's mainly in the ocean. So that is about heat in the ocean. It's about the strength of ocean currents moving this heat around. And so what we are doing at the Nansen Center, we are working with all timescales except for the atmospheric timescales. We are not working on days to weeks, but we are working on seasons, years, decades. And we also contribute to the scenarios that Mikael talked about. And the ocean is like the memory of the elephant. It's a very long memory. Data assimilation, that is about taking the observations, feeding the observations into the models to synchronize the models. So if we think about the climate scenarios, they typically start in 1850 and so, and then they are just run forward in time. They have no idea when there is an El Niño, for instance. They have no idea if the ocean currents are strong or weak at the point, because the models are evolving and developing this without information from the observations. So what we are doing with data assimilation, we take the ocean observations, feed them into the models to make sure that the models are synchronized with the nature. So if there is an El Niño, then the model will have this El Niño when you use data assimilation. And then you can use this model to predict the future, the near future. So both we will have a realistic timing of events in our models, and we will also have a realistic location of where such events happen. For instance, like a marine heat wave in the Barents Sea. You heard about the Norwegian Earth System model. I will not say anything about this, just say this is it's a complicated full Earth system models with lots of different components for atmosphere, ocean, chemistry, biology in the ocean, land, surface, rivers, and so on. So it's a complicated system. On top of this system, there has been made something called the Norwegian climate prediction model. So that is simply to use this climate model, use data assimilation to synchronize this model, and then to run it forward in time. And what we have typically done is to use ocean observations, but we are now extending it, I will just mention in a few minutes. And we are using this system now for quite many types of climate research, climate experiments. So we are doing long climate simulations or reanalysis. So we assimilate data from proxies or paleo data for 1,500 years back in time. We are having integration from 1850 with observations from the ocean, so that's the 150 or 170 years run. And we are also using this for climate prediction for seasons, or months ahead, years ahead, and into decades ahead. And we are now using this model in quite many different approaches. So it's the backbone of a Norwegian Center of research-based innovation called Climate Futures, where we are bringing seasonal data into fishery fish farming, into agriculture, into power sector, into different business sectors. We are producing also seasonal annual decadal data for WMO and for CMIP, so this is the IPCC type of experiments. So we have now a full range of experiments with a full range of user groups. And one slide just to show the performance, I see time is running. There is quite a large skill in the climate system, and just one point of showing this is the right-hand figure. Lots of the skill in the ocean, it is in the North Atlantic. So this is where we actually see that to integrate ocean observations, we are improving the skills a lot. We are making much more accurate decadal forecast, and that has to do with the Gulf Stream, and it has to do with the movement of heat northwards. I briefly mentioned this. We are working on all different timescales. I think I skipped this. I've just showed 3 very quick examples of how we are improving this system now, because we are living in exciting times. There are lots of innovation going on, lots of new improvements. And one very nice thing we are doing now is that we are assimilating more information into the model system. And this is just showing the 2018 Scandinavian heat wave. The first column is observations, era 5. The second column is our climate prediction system with only ocean observations. And the third column is the climate prediction system with soil moisture assimilated. And if you just compare the third with the first column, you can see they are quite alike. So it's actually with soil moisture we're able to reproduce this extreme heat and also drought in Scandinavia in 2018. Very quick, the time is flying. Also what we are doing, and this is very complicated, I'll just say that we are using this data assimilation for automatic methods to improve the parameterizations. It has to do with the clouds, as Trude talked about. It has to do with sea ice. It has to do with convection in the atmosphere. It has to do with turbulence in the ocean. So we are improving the model system with automatic methods, making it much more skillful. And the most exciting thing we are doing now at the Nansen Center and University of Bergen and Norse is that we are actually using something called super resolution. And you all have on your phone, if you take a photo, you can sharpen the photo. And that's actually because there is some kind of machine learning comparing coarse resolution with high resolution, and you can go from coarse resolution to high resolution and backwards using this kind of information. And this exactly the same method is used in data assimilation. We have a coarse model. We can sharpen actually the fields. We can use high resolution observations into this, and we can go back to the coarse resolution. So it's improvement in the data assimilation using new techniques. So this is just very quick, and the cost of this, it takes some 25% longer time compared with about 800% longer time with having twice the resolution. And I skipped this. Just say that we can also use this in the climate model, where we can actually have a high resolution atmosphere with a much coarser resolution model, and we can have them to interact. And finally, to say that all these techniques are now coming into the Norwegian climate prediction system. It's also coming into a Norwegian Earth system model. So we are using this information to improve the model system that will be used in the future for the Norwegian Earth system model. So And time is running, so thank you. Yeah.
Any questions from you? Yes, Hjørdis. Yeah, you will get a mic. Please say whom you are.
Does that work? Yeah. Thank you very much. My name is Hjørdis Tradowski. I'm from the Norwegian Meteorological Institute, and I have a question. So you just mentioned a little bit about artificial intelligence. I have a question because when we look at weather forecasting, there is a really rapid development looking at artificial intelligence for the use in modeling. Now I'm wondering, when it comes to modeling of our seas, how does the development compare? I don't know how much you know about the developments in weather. Otherwise, how fast is it going? Do you see a real revolution there? How is that? Thank you very much.
I'm quite sure there are people in the audience that know this better than me, but of course what I've seen also from the ocean, there is a very rapid development. So there are people now using data and then give forecasts directly without, so it's just simply by machine learning. So it's a rapid development, and the skills are high for these models, but still more like you can take 1 point. So you will not, at least at present, they are not able to forecast the full three-dimensional system, for instance. But perhaps in the future that Yr will have a competition that, of course, then Google may simply use such a system, for instance, to give a forecast for Bergen or Tromsø, probably with the better skills that Roar can. Perhaps. But the development is very fast. I think it's very difficult to see how the future will be when it comes to artificial intelligence. Yeah.
Thanks, Toran, since you challenged me. Parts of Yr will be based on artificial intelligence this year. And Google will also release a model on their side. So we will see who is the best. Okay, thanks, Tore. Our final talk will be given by Priscilla Mooney. Priscilla, she is a climate scientist and research professor at NORS and the Bjarknes Center for Climate Research. Her work focuses on climate science, particularly in the areas of oceanography, atmospheric interaction, and climate modeling. And Priscilla, the floor is yours to tell us about modeling of climate impact assessments.
Thank you very much. All right, so I thought I'd say a bit about climate modeling for impact assessments from the perspective of the PolarRes project. And just to say a little bit about what PolarRes is, the name of the project is the Polar Regions in the Earth System, and the project's been going on for about 4 years now, so we're pretty close to the end of the project. And tomorrow we've got 2 sessions on some of the outcomes of this project. So you can see a little bit more about it tomorrow. It was an EU-funded project, funded under Horizon Europe, with a budget of about 8 million and 16 partners involved. And you can see the logos from all of our partners here, and Metno is a partner in that with us. And so we have a website as well, so you can also check out more about the project, because there's more to the project than just what I will present today and tomorrow. So one of the core ambitions of the project is to improve regional climate information for impact assessments in both the Arctic and the Antarctic. Today I'll maybe focus a little bit more just on the Arctic, given the setting that we're in. And so some of the impacts that we are looking at in the PolarRes project are shown here on the screen. So we are looking at the impact of climate change on fires in the Arctic, on thawing permafrost, marine ecosystems, and extreme events. Yeah, most of these are just listed here. And so one of the key things about what we're doing is producing higher resolution climate projections than maybe you would get in the global models right now. And so that's what this figure here is showing you. So there's a lot of text, but you can maybe just ignore some of the stuff on the bottom. What I'd like you to focus on is the axis, this black line, which shows the different grid spacings of the different types of global and regional models that we have. And so you can see that the CMIP6 IPCC models there at about 100 kilometer grid spacings. And just below the axis, you can see some of the features that we can, and phenomena that we can resolve at those grid spacings. So for example, planetary waves. And so NORI-SM is one of these impressive IPCC CMIP6 models that fits in this particular category. And of course, there have been other international initiatives as well, reaching down to higher grid spacings, such as Polar Cordex and high-res MIP. And the PolarRes project sits here at the 10-kilometer grid spacing, so it's a higher resolution, so we can resolve more of the important features, particularly those that are impactful for society. And so that's one of the things that we are doing. And so the general workflow is very much here on the left that we see we take CMIP6 models for information. So this is where NORI-SM, for example, plays a role. And we use our regional climate models to take a region of the planet, in this case the Arctic, and use that information to produce higher resolution and climate information. So really trying to get down to more impact-relevant scales with our information. And then we work with impact scientists involved in modeling the impacts on like permafrost, for example, and share our information with them. So this is just a general kind of workflow, and traditionally we have also followed this as what I'm saying here is a flow of information. So it's very often that the scientists in these communities, so the global climate scientists, regional climate, and the impacts communities have maybe not necessarily always talked to each other when they design their data and information. And so in part of this project, what we did was from the very beginning, set up an exchange of information to understand the needs of each community and the capabilities. And that was really very helpful in designing the information that could then be used. And also producing maybe information that for the impacts assessments that were previously not produced and turned out to be quite helpful. One of the other aspects of the information that we have produced is we used a storylines approach to look at uncertainty in climate projections. So just to briefly maybe say a little bit about storylines and what they are. So here is a maybe well-known example to everybody. So you can see that future projections of global warming has a wide range of spreads. And in this particular figure, you can see that this spread can be maybe understood from the point of the different kind of pathways that we will take in the future in terms of emissions. So the values can range from, from 6 to 1.5 degree, right? And we can say that if we follow this emissions pathway, that will happen. And if we follow this higher emissions pathway, then it'll be much warmer than that. And so with this storylines approach, what we are trying to understand is, or trying to explain in some ways, is the spread within this scenario. So what are the physical explanations for why our global models are producing such a broad spread in these? And sort of communicating that in maybe a more meaningful way. So that's just a very short answer to that question. And so I will skip this in the interest of time. I see it moving along. So this is what we used in to choose which global models that we would use in our information, developing our climate information. And so based on how the different models projected the warming in the Barents Current Seas area and the different variations of Arctic amplification, we chose our global models. And one of those was the NORI-SM 2 models. And maybe the differences in some of these Arctic amplifications is, as Trude said earlier, how clouds are represented, but maybe also sea ice as well. And so with that, we have an ensemble of regional models from many of our partners across Europe. So we downscaled NORI-SM and the CNRM model with 8 different regional models. So we have HCLIM there from Met Norway and WRF from Norse. So again, well, within the NORI-SM family in some way. And we downscale that over the Arctic and Antarctic. And we are now coming towards the end of the project where we are using this information to assess the impacts in the polar regions. And so just to show you some of the impacts that we are assessing, as I said earlier, permafrost and wildfires, but also marine ecosystems, because we have coupled regional models as well in there, so we've got the ocean and the atmosphere. We're also looking at reindeer herding. I don't know if Hydron is here. Now, this is also in collaboration with the EU Project Charter. Trans-Arctic navigation, radionuclide dispersion in the Arctic, climate extremes, and there are many, many more opportunities to use this data to assess other impacts as well. And so, as I said earlier, we will be presenting some of the results from this, some preliminary results tomorrow, so please come along to our session tomorrow if you want to hear more. And yeah, that's it from me, so thank you very much for your attention.
So when will your project be finished, and will you have sort of a seminar to present all of it, or is it tomorrow we have the chance to see the results?
Yeah, tomorrow will be a taste, maybe, a sneak preview of what's to come. The project ends in August, September of this year, and we'll be presenting some of it in June in Brussels. So,
very good. Thanks a lot. And now it's time for a panel debate with the team. How can NORISM and other climate models help us to prepare for climate change in the Arctic? And I would like to invite all the speakers up on this podium. So you will get, again, your daily exercise by going up on the stage here. And they will also be joined by Rasmus Benestad. He's a climate scientist at Met Norway, and his work focuses on climate variability, climate change, and the development of climate models. So Rasmus is here as well. And as I said at the beginning of this event, we very much welcome questions from you, and also comments to what you have heard today. And in particular, if you want to challenge these scientists, I would be very happy. And also comments on where you believe future knowledge is necessary. So we will have a microphone that will be passed around. Please prepare some questions, but I will start by warming up a bit the scientists. And we can do it, everyone can do it, and Trude, since you are here, let's see, do we have a microphone that can be used here as well? Yeah. You can start. Which climate questions do you think are specific in an Arctic context? What should we work towards answering?
Well, that's a big question, certainly. Well, I think for me, the beginning is always, what in terms of how much warming, what do we have to prepare for, which I touched on in my presentation as well. And I'm hoping that we can aim for NORISM to be the model to trust, the Earth system model to trust when it comes to the Arctic. And then I think it was interesting to see Priscilla's presentation as well, where it's clear that we do need higher resolution, whether we use regional models or we use machine learning to get to the finer scale, which is where the real impacts are. So I think this partnership between Earth system models and either the regional models or now maybe also machine learning is really, really important, and will kind of give people the information that they need on the more local scale. Hope that answered it.
Yeah, good. Pass on to Einar.
Yeah, that's a big question. So for me, what characterizes the Arctic is always the presence of frozen water, of ice in any shape or form. And obviously, I'm mostly interested in sea ice. I think the question, one of the big open questions, is how quickly are things going to change for the ice in the Arctic. How quickly is it going to open up, and what will it mean for the atmosphere and the ocean? And to answer these questions, then we really need to understand how the interaction between all three of them. And these are often small-scale details that have a large-scale impact. So, like you said before, it is important to also consider and talk to the regional modeling teams and try to understand the processes, basis of the process, and how they have an impact on the large scale.
Yeah, I listened this morning to the ARMAP conclusions, and I was wondering myself, since they announced also they want to update it every 2 years now, will it change in the next 2 years? So will there be a new message in 2 years, or can they just copy what they have said this morning? But on the other hand, I think some of the climate model results there, or a lot of results often look at 2100, and I think it's interesting to look in the next 10, 20 years and focus on whether we understand the trends really in the next 20 years, because that's when adaptation and has to maybe plan and know that information, beside the big mitigation question, of course. I mean, we want to know whether it's reversible or not, and for that we need longer integrations, of course.
Yes, so just to follow up, so what I think is needed is, of course, the right combination of observations and models. So that was what I talked about. So everyone seems to talk about their own pattern. but there are lots of new measurements coming from the Arctic, so it's more and more autonomous systems. So with gliders and buoys, and if you get new ways to collect the data, so we can have the data out in real time from the Arctic, and then combine them with the right type of models, so both high-resolution models and also make this into more climate studies. So I think it is in the combination of observations and models that we can make progress in terms of understanding what's going on today and also how the future Arctic will look like. So.
Thank you very much. Yeah, I agree with pretty much what everybody on the panel has said so far. Maybe I should just summarize. But I mean, from a scientific point of view, there's a lot of science questions outstanding. It's hard to pick or choose which one specifically should be addressed or prioritized. But I definitely think that there is benefit in greater cooperation and collaboration, even though we do work well together already. The observations and modelers do work well together. And there is already some good cooperation between like global and regional modeling and impacts. But we could do better on that, and I think we could make more progress on that as well. And I think also, we see emerging technologies like AI and stuff, and there is a need, I think, to also strengthen collaboration there as well, to really meet the challenges that, Arctic is changing rapidly, and we need to respond quickly to that. So that's my comment.
Thank you. I wrote down 5 bullet points, actually. One in general terms, which is the scientific. And it's very important that the NORSM then contributes to the CMIP, runs multi-model ensembles and global climate models to strengthen scientific knowledge about climate change in the Arctic, as reported by the IPCC, and also the know-how within Norway and climate change simulations. And then I want to talk about the local aspect, because I work on downscaling, and we've used artificial intelligence since 1999. Without much success for the future. It works for the weather forecasting, but not for climate change, because things are changing so very much. But local and regional projections should be based on many different global climate models. And we work with hundreds of them and simulations. And then ensemble spread is very important to indicate uncertainty, and NORSM is part of this. But then I want to say that we had a project called SPAR. That was a seasonal predictability in the Arctic region a few years back that finished after it was finished, and it never was actually followed up. And also there's another project called EU specs on decadal predictability. And I think these are areas where we should look into and follow up this work, because it just stopped because it was end of the project. So maybe a greater role for decadal forecasting and seasonal forecasting and follow up on these. And then also we'll say that different simulations than the standard runs. Having NORSM, we can do much more. And we have some recent results, and now the Washington Post is actually getting interested in this, some of these publications on the fact that the rain is falling on a smaller area of the Earth each day. There's been a trend, and why is that happening? And that has to do with clouds and so on. So we can use NORSM to address these questions in a different way, running numerical experiments in a way beyond the standard CMIP runs as well. So, but I'll stop there because I'm just taking too much time.
That's okay, Rasmus, because you didn't have a presentation, so it's okay. But now I've seen a couple of questions from the audience. I think Lars was first. Please state your name and where you are from, and if the questions is from one of the scientists, you may say that, otherwise I will challenge them.
So I'm Lars Kullerud, President of University of the Arctic. I have a question to all of you. You represent a group of science which have been extremely successful. Most of the world, except that the President, have understood that climate change is really serious for the mankind. And Arctic science, the climate and environmental science in the Arctic spend about 3/4 of all Arctic research money, which is at least in this order of magnitude €1 billion a year, of the free competed money coming from research councils. Most policymakers would now say, it's time to fix the problem. We don't need to know more. But you clearly now tell us you need to know more. So how do you want to deal with that problem, that you have been a big success in describing a problem, and then you still say we cannot spend the money on solving the problem, we need more money for us to do more research?
Thanks, Lars. That is a real challenge for the scientists. So who would want to start? Okay.
I can start, since I think I was the one guilty of saying the science is not settled. And so I really do think that we're still dealing with uncertainties that are unacceptable for mitigation and adaptation efforts. And I think that should be clear to anyone who sat in through these presentations. But of course, it's not one or the other. We need to continue to work on research to constrain future projections, to reduce uncertainty. But of course, a lot of resources should still also go into fixing the problem. No question, but I think we do need to prioritize both.
Yeah, you could pose the question also in other directions. I mean, do we need to know more about quarks and strings and atomic structure? I think part of climate science is also keeping the knowledge and doing education and continuing records besides the questions of that we don't know everything. I mean, I think we are still a source of information, and you wouldn't stop cutting out that information just because you know what to do on emissions. We still want to know how quick climate is changing, where exactly, do we understand these extreme events? Can we get to more local information? Planning infrastructure, we need more local information. I think I wouldn't cut climate science. Why don't you cut other branches? Which I
Good.
That was a very good question, and I will just add to the previous replies that what we need to do is to adapt to climate change, so we haven't got that far on this. And also there are some things I think we really need to address, and we just touched upon it, was in the AMAP session, is that the connection between the Arctic and the mid-latitude in terms of the polar vortex and also the jet stream. The models, we get it in the weather models, but not in the climate models because they're too coarse. And we still don't understand how the jet stream and the polar vortex will change in a changing climate. And that affects even as far as Florida and Texas. So we're talking about a lot of people being affected here.
Thank you very much. And just to add to that last comment from Rasmus, this is the question that I get the most internationally. How will the changes in the Arctic affect the lower latitudes? And I think we don't have that answer yet. Tore, do you want to answer as well?
No, so to your last question, I think it's right to say that we don't really know the answer. So it seems that changes in the Arctic is influencing weather patterns, but it's also hard to assess how large is this influence compared to many other things that are influencing, for instance, the jet stream. But it's certainly something that people are looking into. And also, of course, in the ocean, how are changes in the Arctic or changing in the in the Antarctica, how for instance, the meltwater influencing the ocean currents and changing the climate. So there are many things in this polar, extrapolar interactions that it still needs to do lots of research on. So I still think it's too early to cut our budgets, Lars.
Okay, good. I saw that Jan also had a question.
Thank you. Thank you very much for the presentations. My name is Jan Fuglestedt from Cicero. When we were writing the IPCC report that was published in 2021 with Trude on board, one of the emerging topics were overshoot. And overshoot means exceeding a temperature level and returning below that temperature level again. And we didn't have much literature on that. And now that we're approaching 1.5, as defined in the Paris Agreement, averaged over a couple of decades, and countries have net zero targets, and we also need to go net negative. Is NORSM a useful tool for studying the behavior of the climate system in a world where emissions are going down again, and the responses of the different components of the climate system? Thank you.
Thanks, Jan. That's also a very good question. We hope we will get there. So, who?
Sure. I mean, that's the purpose of climate models, that we can test different scenarios. And the question whether they capture reversibility of carbon budgets, I think that's a science question which you have to study. I mean, we have changes in the past. In the last decades, we get more and more experience getting into the future slowly. So we have more records of changing ecosystems, changing physical systems. So if we use that clever, I think we will also understand whether a reversal of emissions will have an impact and how quick. I mean, that was the result of the 1.5 versus 2 degree report, that the systems, the models react in a certain way. They take up heat and carbon and amplify emission reductions eventually, if that's correct.
Anyone else? No? Or?
Yeah, so of course one issue with the overshoot is of course the risk of tipping points that are increasing and often increasing exponentially if you come above some threshold. So of course that is possible to study in models, but also I think it's fair to say that the models they are useful, but they are not telling us the right answer or the exact answer. So if you think about the forest being replaced by desert sand, for instance, that's typically tipping point that's hard to go back. Even if you lower temperatures again, you're not coming back to the state you had before you had this overshooting. Or it may be biological changes in the ocean that if you are destroying a coral reefs, you are not getting the coral reefs back, even if you come below 1.5 degrees. So lots of things to study, and there are lots of risks that are amplified with the overshoot strategy compared to keeping the warming below a certain threshold. So.
Thanks. And Tore, now you mentioned tipping points. And you can keep the microphone. Because at the Arctic Circle conference in Reykjavik last October, 44 experts on ocean circulation warned us about the risk of regional cooling around the North Atlantic as a result of the weakening of the Atlantic Meridional Overturning Circulation, or AMOC for short. Can you tell us, what are the facts about the AMOC and what are the risks of a regional cooling?
Yeah, so the answer to the risk will depend on who you ask.
Okay.
So it's lots of research going into this. What happened to the large-scale ocean circulations in the North Atlantic with global warming? And that has to do with melting of Greenland ice sheet and more meltwater. It also has to do with warming of the northern regions that is making the ocean water lighter, and also so it's harder for the ocean water to sink and keep up this motor or engine for the Gulf Stream and the large-scale systems. In all climate models, the strength of this overturning system is weakening in the future. And if you run the models past 2100 and into 2200 with the high emission scenarios, then the AMOC more or less disappears. So it goes towards zero gradually. And that has an effect that it's a region in the North Atlantic that is getting much colder than the rest of the globe. So it's the reduced warming, and even some models there is a slight cooling in the future due to this effect. But I am not among those that are most scared, because this seems to be an effect, at least according to the models, this is the effect that will be gradually into the next 100, 150, 200 years. But there are people who are claiming that the models are not very good to simulate this, that the models are too conservative, they are changes too slowly, and that they are afraid of that there may be a much more abrupt change in the AMOX, and that there may be cooling ahead for Northern Europe, for instance, instead of warming in the future. But again, I think it's hard to say. There are lots of research going into this, and there are different opinions on this, but I am not among those that are most scared, because I think there are so many other things with climate change that will make much more harms to the planet and to the nature and societies before this AMOC thing. But that's my opinion.
Thanks. I think Trude would like to comment as well.
Yeah, I just wanted to say I tend to agree with you, Tore, but I also think that our system models, while they have improved a lot in recent decades, they're just not up to the task when it comes to tipping points. So we know that there are missing processes or poorly representing processes that are underlying mechanisms for tipping points, whether it's AMOC or other proposed tipping points. So I think this just highlights that we still have a long way to go if we want to trust our models when it comes to possible tipping points and assessing the risk of that. And I also wanted to say quickly, in response to what you said, Rasmus, about the importance of having model ensembles, I totally agree, but I think it's also true that we're in some ways moving away from model democracy now, and sometimes we can show that some models are just not credible in certain regions, for example, the Arctic, when this has been done with Arctic sea ice, and I think we should have the ambition with NORISM to be the model to be trusted, or being among the models that we can trust when it comes to Arctic processes.
Yes, please, Rasmus.
Thank you, Trude. I'd like to respond to that, because that is very, very interesting to actually understand why the models fail. We can learn a lot from that. It's actually maybe easier to learn from the bad models than the correct models. So I think there's a value even in bad models, but I agree completely with you. I just wanted to make this point.
Thanks. Please raise your hand if you have more questions. Yes, Jordis.
Thank you very much. So yeah, another question from Jordis Stradowski, Meteorological Institute. I think we saw in all your wonderful presentations quite clearly that there are still puzzle pieces to solve for the Arctic and for climate in general, and that by solving these puzzle pieces, we actually do get better with predicting what climate will bring. But now my question is, how can we make those results where we can already show a lot of value in these results, how can we make them better understood by a wider range of policy and decision makers? I mean, not every commune has a climate scientist that can help to understand the results. How can we make them better understood? And are there maybe some really new approaches, some maybe really innovative new ideas that you have in mind, that you have discussed with colleagues? Is there something that you would like to share in that regard? Thank you.
Thanks, Jordis. Rasmus would like to start.
A few years back, I made a discovery that the Washington Post, they made some wonderful stories about climate change, and they tell a story from a scientist traveling out to Antarctic and how they measure and also that they bake into this the problems and everything. So rather than throwing facts at people, you had to tell a good story, and you had to make people interested. And from that story, people also understand like what is at stake as well. And I think also we have failed to communicate. I think the IPCC has failed to communicate. I'm sorry, but I think we as scientists have failed to explain and tell the people this. Yesterday I sat at Ølhallen and talked to some fishermen. We had some beers. and they asked me if I was a tourist. I said, no, I'm Norwegian. Where do you work? I work for the Norwegian Meteorological Institute. And I said, I started talking about climate change, and they was a bit skeptical, said that climate has always changed. I said, yes, that is right. And you know what? The reason is because the climate is really sensitive. And then we had this really nice conversation, and we had to talk with people, not talk to them. So I think it's an issue of communication. I think the IPCC has failed completely. Sorry about that.
I think Trude was first.
Well, I have to disagree a bit with you there in terms of the IPCC having failed, because I was inside the process last time around for the last report and did interact directly with policymakers, I think for the first time ever in my scientific career, because it's not something that is generally accessible to me. And I think it was a very important conversation and very fruitful. So I think there's really important processes initiated by the IPCC. But I also wanted to say, since you asked about maybe novel or kind of different approaches, so, it depends on the audience, of course, what kind of messaging you want to do. But we've developed an educational game on climate change that we can use for students. So I think that's an example where we try to reach people in a different way than, for example, what IPCC does.
I think that analysis is too simple. I think the problem is too big. I think without IPCC, without assessment reports, we wouldn't have consolidated factor to which you have to respond to. But the question from your audience is certainly correct. I mean, important. I mean, how to communicate in the future, how to process data differently, or are there maybe gaps in knowledge? But if somebody doesn't want to listen, you can talk however you want. I mean, I think there are so many interests involved that IPCC is just one important talking institution, and there are other institutions which talk against and have other interests. And I think that struggle is very different from, let's say, acid rain, where assessment and assessment reports had a great impact, and that was economically feasible to clean up the air pollution. It didn't hurt, it gave benefits directly. And I think one has to maybe forward the benefits of reducing emissions, get everybody on board for climate emission reductions. And I think that's not just the job of IPCC, and I think that's why IPCC as such didn't fail. I think it's a source of information.
Yeah, so perhaps quick, so I also will disagree with Rasmus. I think IPCC has done a great job, and of course it's due to IPCC that all the world leaders got together in Paris to sign the agreement. So it is due to the IPCC and this very thorough process that we have got the international policies on climate. And then of course one could say that there is still many other people around that to be convinced, and yeah, it could be a long debate about fake news and all the disinformation that is out there, and it seems to be increasing in strength. So that is perhaps the major threat when it comes to making changes to policies or changes to people's behavior. So that's a big discussion. But I would not say that the climate community has failed, but there are lots of resistance out there.
I must make a nuance. I agree it hasn't failed. The IPCC has played a big role, important role, but still to explain to our politicians and also to Donald Trump and those who voted for him, we didn't succeed.
So maybe if I could make a comment and follow on from what Mikael said. It is quite complex. I don't think there's a simple answer to the question, but it's an important question. And I think from my own experiences, maybe one way we could do better is, because I'm a climate physicist, right? So communicating and understanding the backdrop of which policymakers make decisions and formulate policy is definitely outside of my wheelhouse. And I think a greater, maybe, and we already work quite closely with
the scientists who work in that kind of area in policy making and understanding that. But I think maybe more of that is what we need. And so I think maybe also, just to come back what I said earlier, maybe all of us said it, greater cooperation, not just between us as modelers and observations, but also maybe greater cooperations between the natural and social scientists as well in understanding how to communicate better to that.
Yes.
So.
Very good point, Einar.
Yeah, just to add a bit to this, I think we have more or less explained to everyone who's willing to listen. It's sort of that's what it feels like, and the question to me becomes: why should people really care? I mean, what do people really care about? They care about their immediate future, their immediate prospect, and they care maybe about the prospect of their children, and then they start to care about larger scope things. So we need to put this square in their interest zone. Really, this is about the future of your children and your children's children. And things are going to go really bad for these people that you care about unless you do something. It's a bit of the scare tactic, perhaps, but it feels like all the science has been said. We've told all the good stories. We've done what the Washington Post has done very nicely, and we do it again and again. And we still have people like Trump and their followers. I'm a bit lost, actually.
Are there any final questions from the audience? Yes, there is one.
Yes, I'm Leif Einar. I'm an advisor in COAT, a new research center here in Troms, working with Arctic climate change and the tundra. And I wonder, you talk about observations to improve the models. Are there certain observations that you lack? And are some of those coming from the terrestrial ecosystem?
Thanks, Leif Einar. Who would want to answer that question? Tore is giving it a go.
I felt that you were looking at me. No, so certainly if you think about the ocean, I can start with the ocean, then of course everything that's going on underneath the sea ice, and especially in winter time, that is more or less unmeasured, or there might be some point measurements. So I think to get much more autonomous systems underneath the ice and in the open Arctic will be greatly improve the models, perhaps also even the atmospheric models, if you think about leads and taking this into account. And then when it comes to tundra, it's not my field actually, but if you think about the war going on now and the difficulties of getting data, or at least getting access to a large part of the Arctic, I think that is a problem. But again, I'm not expert here, perhaps. Trude.
I'm also not an expert, but maybe I can speak on behalf of my colleagues who work on permafrost, for example, and I know that they're desperate for more measurements, and especially maybe on the Russian side of the border, where they now don't have any access to measurements. So absolutely on land and the tundra, there's also need for measurements, and also fluxes and so on. I want to say in general, though, with measurements in the Arctic, we're getting access to more and more of it through satellite observations and also field campaigns, which is wonderful. But I think what is lacking still continuous monitoring, continuous measurements, so that we can look for trends and look for persistent patterns. It's hard to get funding for that kind of measurements, though it's easier to get funding for episodic measurements, a campaign. But what is really needed if you were looking for climate change is, of course, long-term monitoring.
Yeah, I absolutely agree on the long-term monitoring aspect. That's crucially important when we're trying to understand climate change. What I wanted to add is that we are sort of, feels like we're entering a golden age of satellite observations. We have a lot of satellites going up, and a lot of this information is freely available as well, which was not always the case before. So satellites, obviously, you only see the surface, so you can't see the deep ocean or the tundra, deep into the tundra, but there's a lot of information there coming today and will be much more in the future. So I think that's a really positive note for us.
Okay, it's 12:30, and it's time to close this session. I would like to say that the discussion we had on communication here, I think, is very important, as well as we have learned a lot about the uncertainties that are still in the models and that we need to work on, and also the fact that what's happening in the Arctic may or may not have significant influence on lower latitudes, and that's also a topic to work on. I would like to thank all the presenters and panelists for their contributions, and you for joining here and asking questions. Thank you to everyone.